Hi, this is Bill Foote, and it is week 4, very beginning of week 4, in our course on system dynamics, uh, inferring our results using Bayesian data analysis. And from this week forward, we're going to be spending a lot more time looking at a screen like this, actually working the model directly in this RStudio integrated development environment. You can see I've already started this as with the YAML, yet another markup language, between the 3 hyphens or dashes. And all this is quite strict. It parses it exactly this way. We'll have a system date. I have a bibliography that I'm using. There's only two items in there right now, but I suspect I'm going to add a few more as I go forward. Um, the output in this particular case will be an HTML document with a TOC, a table of contents. It'll go to 3 depths inside of this. I only have 1 in here right now, but we'll see how that goes. And then the rest of this is R chunks. These are tick marks with R. That's the language that will be interpreted inside of this code chunk. And you don't have to worry about knitter and the offset, except I usually set it to message equals false, warning equals false. Nobody needs to see that but us who are developing. I'm going to be using tidyverse and R thinking. There's another one down here, and I might use a third one. Library, I've already introduced this to you. Plotly and library. Now this is a C++ real fast, thus R fast, way to do certain arithmetic operation on arrays. The one we're going to be interested in using is a column product. So column-wise products, you take a column of numbers and produce 3 numbers, 1, 3, and 5. It will be 1 times 3 times 5. And this, remember, is how we did our likelihood functions. Yes, the probability of data given a particular hypothesis. We will do that below, and that will be the brute force that you see. Now, um, the pretty view of all this is going to be up here. I don't want to look at that yet. Counting on Laplace. This is how it's going to look basically. Right? A little bit easier on the eyes. We're going to go straight into making a model. We've already seen this model a whole bunch of times, and work this model in paper and pencil format. Very helpful for us to do that, because all the rest of this looks like, I don't know what you want to call it. You got arrows and things going all over the place, and it takes a little bit of a different point of view to go through this as opposed to paper and pencil, and certainly not Excel. And we're going to be making graphs. That's a nonsense graph, but that graph works out to something like this when it's not nonsensical. So I have a little example here called Bronx zip codes, which is part of the counting the ways reading. It was built during COVID. No, it was actually built it wasn't the Bronx, it was counties in New Jersey the first time I did this with Ebola. Okay, minor details there that, maybe we can go into. But I want to actually, instead of look at this, let's focus on the environment that we'll be making this in. Okay, there may be others that we'll add. If you haven't already, do this. There we go, install packages, concatenate coda, mean variance, tn norm. Stands for students, T, and norm is the Gaussian or normal distribution. If if these terms are not familiar to you, go to my statistical thinking site in the resources and refresh yourself. Better yet, look it up on Wikipedia. There's very good articles there. Dev tools, Lou is leave one out, which is my preferred way to do cross validation. That's a training and out of sample approach to a machine learning problem. Daggity, we may or may not use Daggity, but Richard McElreath does, and I love it. I mean, you go to daggity.net and make your own causal diagrams. Okay, they show you how to do that there. If you haven't already, put in rethinking at slim. Now, in order to do that, you use dev tools. The double colon here says that that's the package. Look inside the package for a function called install underscore GitHub, open parentheses, in double quotes, RM McElreath, which is Richard's GitHub site name, backslash rethinking at slim. We want the slim version at this juncture. Next week, we will want the full shot, but some of us might not be able to get that on some of our machines. Okay, I fully understand that because that's when we walk into Stan and do some very serious damage to our certain neural paths. But basically, wake up. Patient wakes up and oh, I feel great now. What did you do? Well, we used Stan. That's what we did. And Plotly for interactive plots are fast for the column print. Okay. So again, there may be other ones, but Coda is one that we will be using as we go down here. Brute force, grid approximation. Again, very well described in Count the Ways. But here we are. We don't need these. If we have those up here, just let me make sure I do have these there. I don't need to reinstall this. And I've got this and this. Notice in this version, you're going to get, and that's why I did this, you're going to get messages, okay? When you actually compile this and render it in HTML or PDF or whatever, you don't get these messages. You also don't get any warnings. There we go. This is a very easy to use approach to Bayesian anything. A lot of modeling happens this way. And here I'm going to use something else that you might not remember very well, the binary choice binomial model. It's a 0 if you don't do something, it's a 1 if you do. A success is a 1 usually. That's how we usually code it. But we're going to do this 1,000 times. Now, paper and pencil, you don't need to do that. You can do it 2 times or 3 times, but 1,000 times? No. And that's the beauty of what we can do here. We can make a larger scale simulation of what is called a very small world. Okay, after all. Anyways, that's from Walt Disney. N success, the number of success. Notice I'm using the underscore approach here to naming variables. Number of, and that's how I read it, N of trials, number of trials. This is binomial speak. The binomial model, my favorite model. You take that model, which is really Pascal's triangle, line it up with the on series called an EXP, the natural exponent series, and you probably have all of math, nearly all of it. The rest is linear algebra, as some people say. So it's a good thing to know the binomial model. And again, the introduction to that is in, where is it in? Count the Ways. And We also basically did this when we did the 0, 1, 2, 3, 4, 4, 3, 2, 1, 0 combination. 0, 4, 1, 3, 2, 2, 3, 1, 4, 0. I'm not even going to show it to you. Go back and look at the notes from the previous lecture, and you'll see it there. That is the binomial model. You got to unpack it a little bit, but it's the same thing. We're using a Tibble, which is a subset of data frames. Create a grid from 0 to 1, length out, length of 1,000, something we'll call a P grid. The P is, okay, how many times do you get a 1 if you have 4 shots? It goes from 0 to 0.25 to 0.5 to what? 0.75 and then to 1.0. Okay, again, we did that already. What we're doing now is we are just setting up a model and thinking of it this way. Okay, line by line. We also had the prior distribution of these hypotheses. Okay, there's quite a few of these. There's a lot of these. N is 1,000. Okay, we don't need to do 1,000 of these, but what does the N really stand for? If the length out is N, number of hypotheses. Let's switch that out to, I'm going to do something a little bit different here. I'm going to do the number of hypotheses as 11, just to make it a little bit easier to read. There we go. It is that simple. Wow. Okay. So that's true. That's true. Number of successes, 2. We have 2 positive results. This is vaccines. Yeah. Anyways, and we tested, got these results out of 8 different locations. The prior set at 1 means it's just equally likely. If we were to put in 1 over h, it wouldn't matter. Okay, it wouldn't matter. And the reason it wouldn't matter is that our analysis is each hypothesis is relative to another. That's why it's in the math. And then we use a function called mutate to calculate a likelihood. And here the likelihood is a binomial density and success over p trials. Okay, let's just take this thing out here. Pop it over here in the console. Okay. P-grid not found. So if I do p-grid as see what I'm doing, I'm playing with it. Play is really important. It's how I that's how I learn mainly. Okay, and p-grid. Look at the p-grid. There's 11 of these from 0 to 1, 0.1, 0.2. Okay, it knew how to do that automatically. That's what the sequence function does. And if we do this, there we go. Now we have our binomial probabilities. Already you can see that at low ends of the p-grid, okay, it goes up to 64, and then it starts to drop. So 1, 2, 3, 4. After the 4th, when it gets to the 5th, and there on out, it starts to drop like a rock. Of course, it goes to 0 here. Okay. Now, I know that when I do this in Excel, I have a problem with this density function at a p-value, which is the probability of a single up move in a binomial process, a single success. It has problems with 1 over here. Okay, so there we go. So, but this is how you play with it. 9, 10, 11, or 11 of these because there are 11 p grids and success and so on. So, okay, the mutate says make a new something called likelihood, and then do another calculation. So this is just a calculator inside of a data frame. That's a good way to think about these things. These things being her calculations as being data in a data frame. Not just the raw data that we typically think of, but data and calculations. And as you can see, well, we should be, every single one of these lines practically should be commented. But that's the educational problem. And we're educating ourselves all the time, whether we're at the job or here. Posterior is equal to the likelihood times the prior. Now, your job at this one is to go back to what we did before on a grid and see how this works. See if I can bring this up quickly here. Nothing on the plus. I had it here, honest. Oh, I got all sorts of stuff here, don't I? There it is. Here's the Adobe scan. Oh, this is something else that we haven't talked about, but it's the same idea, where is lambda, okay? And here's the prior, all the same. Here's data. And what we just calculated with d binom are these kinds of numbers over here. And when you multiply this times this times this times this, you get this, all right? And then we add them up, and lo and behold, we've been able to figure out the probability of a hypothesis occurring given the data, all the data, okay? This row mashes together all this data and this one hypothesis into one number. This is where the product occurs. And of course, do some graphs always. The thing that we did on our own was this, remember. Hypothesis, data, and this is a two-way contingency table. Okay, everything we needed to know how to do in Bayes is literally right here. Well, there's one more thing, but it's all right here based on this. A nice little algebraic result. Here is just two hypotheses, 3 data points. Same idea. Do this here before you go to R. Okay, well, that was fun. That was decision making. Yeah. Oh, yeah. And what we did originally was this little exercise. Again, back and forth. There. Likelihood times prior divided by that sum of the likelihood. I wrote this out completely just so you could have it. And if I do this, I'm doing Control Enter, by the way. I get a nice little summary of everything. Here's the grid from 0 to 1. It uses first and third quartiles, right? The 25% quantile with an N. 50% quantile is the median. The median and the mean are the same. This is very symmetric. And this is the 75th percent quantile. Gives us a max and a min. Good description. We can do better, but that's really good. And then we get the likelihood. These should be a little bit familiar, but notice how it just banks right up to a max. Okay, this is not a distribution. They're quantiles. And wanted to see this, we can do something like this. Suppose we wanted to make 10 samples, 10,000 samples of a lovely little sign up there. I set the C to 42. Yes, Hitchhiker's Guide to the Galaxy, if anybody's interested. The answer is always 42. And you can make it 42, 42. There's no such thing as a random number. This is very Aristotelian, very mystic as well. Um, Nothing is truly random. Everything has a cause. It's just that we just don't know it. We don't know what the cause is. Okay, ignorance uh, basically says we have two kinds of knowledge: systematic and unsystematic. The unsystematic looks like this random thing, noise on the TV set when you don't know how to push the buttons right to get the cable in. Yes, that's true. Um, but when we produce random numbers, we use what is called a pseudo random number generator. It's an algorithm. And when you put the seed in, like 42, it will come out with exactly the same random numbers every single time. Now, does that sound random to you? Nope, not to me. But what it is doing inside the algorithm is indiscriminately picking stuff out according to the algorithm. You just have to know what the seed is. That's the ultimate crypto key, isn't it? That seed. And yes, indeed. So we're going to take samples. I'm going to switch these over to this. This is the new piping. Okay, D goes into sample N. I take in samples. The weights are the posterior probabilities themselves. Let's write out the posterior. There we go. How come there are only two? This should be it right here. Oh, because I misspecified it. I said D it's inside a tibble. Oh my goodness, I keep forgetting how to do stuff. And there we go. Well, that's more like it. E minus 1 means decimal place. Okay. 0.26 is what this means. And we can fix that. You can use options to make the digits equal to 2 or whatever you want to do. Okay. Options is the answer there. And so here the weight is this posterior distribution. We can take a glimpse. Okay. First of all, let's do this. Now, why are we doing this? We're using this posterior distribution to create samples of all the ways in which we can get 2 out of 8, 2 successes out of 8 tries, 8 trials, 8 times we go out and sample the Bronx. Okay, and the glimpse gives us nice how many rows, how many columns, what kind of numbers. These are double numbers, double precision numbers actually, and we get the grids, okay, and we get priors, and we get all sorts of things, okay, 10,000 of them, and now we're going to make a small plot. You know, Y label, X label, samples, and we're going to do sample number is from 1 to n. Now, in the Tibble tidyverse world, n is a count of how many are in the sample. That's the idea there. What this pipe does actually, worth noting, the vinculum there. It says take this object samples and put it inside these parentheses right there. Okay, that's what it's doing. And we create the cloud of unknowing. Now alpha gives you, that's 1/10, gives you the strength, uh, saturation, if you will, of the color or the black and white. It'll give you a grayscale, for example. Okay, and we can put limits in it. And there we go. And now find function samples. There we go. It's taking a while to do this. There we go. It used to be a cloud at one time, but it's not because it's actually taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's taking the 11 hypotheses. And you can see some of these hypotheses are very, very sparse, and others are very thick. Exactly what you would expect. But this isn't very helpful, actually. Let's make it a little bit more helpful. The frequency in the wave. Okay, so take this diagram and transform it into a frequency. Let's do this. There's a library called TidyBase that we'll be using. Uh, it does the mode, for example. And, oh, beautiful labels and titles. Okay, we're going to do the same thing. P or PLT, whatever you want for your plots. I usually use P. And I'm going to show you one more thing in a second, that is. There we go. Now I'm going to use the Plotly machine on P. Make sure that comments out. But all of this stuff. Okay, we have density. Uh, we have on the x-axis, this is the canvas that's being made with ggplot, the p grid, the 0 to 1 by 0.1, 11 items there. Um, uh, with density, we're going to fill it with blue. Alpha, 0.3. Okay, very low saturation of the color. So that blue isn't going to be that intense. Scale X continuous. You can do things like this. Sometimes I just use XLim for that. V line, we're going to make a nice orange line on there because that'll show up against the blue, I hope. Or maybe I'll make it red. I don't know. Annotate. I want to put a piece of text in. At coordinates x equals 0.5, y is 2. So you got to know how this works. Sometimes you have to work back to this and create a label. Case 0 effectively does a concatenation of this and this. Okay, and concat, that should work. Let's try it over here. I always used to use concat. Nope, nope, I did something wrong. Always doing something wrong. There we go. Concatenated them together. In fact, let's use concat. I don't like paste stuff. Okay, let's see if that works. And a title, and we're going to use this ggplot to do the interactive graphics. So let's try this again here. And lo and behold, as we wait, there we go. Exactly what should have happened. Now, if I used 1,000 values in the P, I would be able to get very nice pieces here. So I'm probably going to switch this density to, let's try this histogram. Oh, there we go. Geom stands for geometric object. Um, there we go. Let's try this. This might not fare well either. I don't know. Again, I'm playing with it. Yeah, that's a little better. Okay, the binomial. Boop, boop, boop. And there are ways in which you can play with the axes to make them. Now notice this is a count over here, not a density anymore. It's the count. All right, and notice this goes over here, and this probably should be put up here around 2,000. 0.5 and 2,000. So let's fix that. Yes, this is what you do all day long in analytics. Play with the numbers and the draw, because the most important thing is nobody's going to be worried about all that other analysis. They're going to be worried about what does this say, and what does map mean? What does map mean? Maximum a posteriori. Well, we can say that, can't we? Are we allowed to say that? Map equals maximum. Okay. And that's the last thing I want to do. There. And then somebody's going to raise their hand. What is that? The maximum. A posteriori is, this is the posterior, the result. It's by, each one of these is a uh, hypothesis. Oh, actually, not, that should be 0 there. It should be 0 here. Good. Okay, and this is the test. Well, that was fun for me. I hope you got a little something out of that. But now I want to move into a different version of all of this. We're still going to do optimal values of posterior parameters. We're going to use something called Laplace's. That's actually not 1902. That's the date of a translation application of his probability, philosophical probabilities, actually. And what he did is he did exactly what we did right here, a version of this with a lot of calculus. We're using a numerical approach that's based in simple algebra, actually. I think we can put all of this into an algebraic framework directly. There's a lot of move to do that because algebras um, are a little bit easier for a lot of us to understand and then use inside of this very machine, this numerical machine. So we may be going in that direction at some point, but all I see is calculus out there. But these would be all derivatives. What I'm pointing at right here. Okay, uh, numerical. The name Faulhaber ought to come up. Faulhaber. Probably was the one who actually invented derivatives based upon sums of integers. But this is algebraic, the whole thing. Algebraic, more algebraic, algebraic. This down here is definitely very algebraic. Okay, Yes, we use probabilities and e's and all of that sort of thing. But the e's themselves, which in this case are expectations, and the l's, which are losses, are operators. PR is an operator. All of this has operational capability, which means algebra. So we'll be going into that, and this definitely is algebra. If you put in A, B, C, D here, you can work out everything algebraically and create an algorithm to do this problem same way all the time, whatever the numbers are. And the same with this. And ultimately, when we get to what we call credibility intervals, which we're almost there. We're almost there right now. But what you notice about our curves, they're going to be effectively looking like a Gaussian curve. And I didn't write it out here. I will probably put that into the document itself. But basically, this is a quadratic equation. It's quadratic. Why is it quadratic? Well, if you look at, let's see if we can bring this up over here. If you look at the distribution that we're really going to play with next, oh, that's so much prettier. Look at this. Within this range, it looks like a bell curve. That's the idea. And there. Forget about this circle trigonometry stuff here. All right. Exp of, I consider this an operator. Mathematically, this is an operator to me. This is an expression in y squared minus 2 mu y plus mu squared. That's a quadratic expression in y. Okay, that's why this is going to work. What's going to happen next? All right, so we will be playing with this. Look up in the sky. It's George Reeves playing Superman. 1955. Yes, Christopher Reeves, the sun. Yes, that's right. Called quadratic approximation. A lot of the algebraic world ultimately will look quadratic. The Pythagorean theorem is a quadratic relationship. And it's enough to describe enough of our reality that we can use it in a lot of situations, as opposed to the grid. Now, we can use the grid for a while, but if we have 20 variables, we're going to have a problem using the grid for all sorts of reasons, which we're not going to get into right here, right now. But the Gaussian shape is indeed just a quadratic shape. Okay, we know how to do quadratic equations from high school, thank goodness. If you don't, go back and look at it. It's great fun. I'd love to have a discussion with anybody about that. Okay. Now, the observational model, which is our model of probability of data given hypotheses. Hypothesis here will be mu. It will also be sigma. Both of those feature inside of the Gaussian model. Okay, there's some math involved. We're multiplying two probabilities together, probability 1 and probability 2. Maybe I should do it like this. Probability 1, probability 2, probability 1, probability 2. Oh, likelihood. I mean, I got to be careful about the language. Richard McElraith has a lovely video on this issue in our discipline. Oh, we get a typo here. Let's fix that while we're here. Okay. So we can use this in a lot of things. Okay, so we're going out of what is definitely first gear. We're going up the hill, right? First gear, standard shift. We're going to go into second gear now. Third, fourth, and fifth gear are in the future. Um, and don't fear that. Okay, future events appearing real. Don't worry about it. We will get ourselves through it because we're going to do group participative transformation here, GPP. That's how we'll do this. Okay, we're the group. We are our own AI, right? Well, we're HI. Anyways, back to this. Suppose I create. Here's the 4242 coming up. Uh, 1,000 numbers uh, using the normal distribution with a mean of 6 and a standard deviation of 2. Now, here I'm looking at a marketing problem. We've been looking at price predators. I'm just going to say price predator, the Wolf Co. company. Price working their magic on Moose Co. customers. I'm thinking of a company in Maine, actually, on the coast. Anyways, that's another thing. And they poach how many customers per month. Well, we're going to measure this with customer hours per month, a duration number, very nice, easy number. I use customers per month. I would probably, instead of using our norm, I'd use our Poisson, the Poisson distribution. Neither here nor there yet. Yeah, we will. It will come up soon enough. And this basically says 6 hours per month with a standard deviation of 2 hours per plus or minus 2, and the number of standard deviations. And here we have the mean and the standard deviation. And notice that when you do some expression like this, it gives the column is creating literally 2 columns here. A mean and a standard deviation of 594 and about a 2.05. That's the data. Very synthetic data is what we're going to be calling it. Some people call it toy data, fake data. I do not like that language for all sorts of reasons. We're technical people. Let's give it its technical name. Okay, I'm going to have to take these off eventually. But this is what our model is. Y is sampled from, notice we use sim in the LaTeX format, from a normal distribution with a mean and a sigma. Well, the mean, in turn, gets dumped in here. It is sampled from a normal distribution with mean of 1 and standard deviation of 10. And the sigma from a log normal distribution, 0 and 10. Now, log normal is important here. We could also use the exponential one. We also can use a beta 1, 1. Anything, sigmas cannot be negative. They must be positive. Okay. We also use a uniform distribution. We use all sorts of things. It's lovely to be able to think this way. Okay. And now we have this, and this is the eGADS moment, right? There should be a negative in here. Whoa, that's a big mistake, buddy. Let's do it. Right. I think I want to do it here, but it's correct to do it here. There we go. Now that's correct. Okay. This is the famous heat equation solution. That's Poisson solution. And Laplace, harmonic functions, yes. Yes, but we're not going to do quantum mechanics today. Oh, we all use the same language. Why not? Okay. But this will be our observational distribution. This is all going to boil down to our expression called d-norm, D-N-O-R-M, period. There it is. And we're going to use the log version of it. Now, hold on, strap yourselves in a little bit here. We're going to create a function. And we're going to use this function in an optimization routine. Because what we want to do, way back up here, remember? There. We want to find the max. That's an optimization. Ours is going to be a lot smoother than this. Oh, yes, it will be. And we're going to find the max. We're going to find the mean and the standard deviation that gives us the largest, okay, the largest number up there, posteriori. Now, how do we know it's a posteriori? Let's look at this. When we take likelihoods, we do sums now. We do logs, rather. We do sums. So the likelihood is a product of the d norm, the parameter, the d norm of a parameter, the log norm of another parameter. But when we do it in logarithms, log equals t, exponentials become sums. And the arithmetic is a lot easier for our tender machines here to handle. And so what we want to get here is log likelihood. Now, if we didn't go any further than this, this is called maximum likelihood here, for those of you who might know what that term means. But no, we put some constraints on it as to how mu and sigma can evolve. They evolve with these prior expectations. And we create a lovely little function here. And when we test the function, let's see if we can do it this way. Get a negative number. Big negative number. If you take this negative number, let's take a number like this, exp to the negative 5, let's say. That's what you get. It's a number, when you get a negative log number, a number between 0 and 1, just prove myself. Minus 0.5. Yep, there we go. There we go. We're getting closer and closer to 1. Notice what's happening, all right? And we could play with that all we want, but what we want to get to is use this in a optimization. Here's the optimization routine. Very straightforward. We initialize it with 0 and 1. Mu and sigma is what we're looking for. We don't care about the data anymore, except as they give us mu's and sigmas and probabilities. That's really what they are, log likelihood. That's what the data is about now. The data is buried inside of all those calculations. We're going to call this thing fit, and we're going to use an optimization routine inside of R, give it inits, give it log likelihood norm. That's the function. Do a little bit of control. Don't worry about what this means. And we want a Hessian. We want something called a Hessian. These 9-foot tall, huge soldiers coming out of Germany. Imagine where that is in Germany. And y equals y is the data. And we're going to come up with this, and let's see if it works today. And we're going to, the answer is 5.93 and 2.047. Awfully close to what we got up there, right? Oh, yes, it was. And now the Hessian is we have mu and sigma with a diagonal. And notice the Hessian is symmetric around the diagonal. This is a number that's used to do the various, kind of like quote unquote hill climbing routines. There are a lot more than that. Broyden, Fletcher, etc. BFGS and Delpho channel and so on. We have a lot of routines to get this done. A lot of people worked a lot of years figuring out those routines. They're called algorithms. And the Hessian is part of that. because it's a 2 by 2. If there's only a 1 by 1 here, you just see this top term. But no, we have two parameters and they interact. Now, if we take this number, this Hessian matrix, okay, no, there won't be any exam on this. Right, but I think you need to know what's under the hood. There we go. There we go. We have something called the variance covariance matrix, and now I feel like I'm in my first econometrics course, where we're doing all of this using Hogg and Craig and Jan Comenta and Henry Thiel and the whole crowd of them, and my favorite Arnold Zellner, where I learned Bayesian from. Sigma, I mean, these are practically zero correlation here, zero covariance. These are variance numbers on the diagonal. And if you perform this little not diagonalization, pull the diagonal out, you see we get the same numbers that we would have gotten, that we're going to get next when you come to this. Keep these in mind, okay? Now, we should be making, this is the rest of the story. All this is going to be boiled down to something very easy to use. So rest assured, we will get there. Make some samples from MVT norm. Now, MVT norm is a package with a library, a package of, pull them off the shelf here, of, in this case, mean variance norm. Okay, it's a multivariate norm, normal distribution. We have two variates, mu and sigma. And we want to do this 10,000 times. Here's the mean. And here is the variance covariance matrix that we just created. How nice. What was the mean again? There we go. The mean is, it's got two elements. One mean is for the mu, the other is for the sigma. Okay, mu and sigma. That wasn't it, was it? Oh, that was a diagonal. I need to pull this back up because it's 5 point something, right? There we go. This is the mean, that is the mean of mu, the mean of sigma, 5.94 and 2.05. And that's what we're using here in our simulation. We did all that optimization just to come up with effectively 6 numbers. A variance covariance matrix with 6 and a with 4 and 2 numbers in the mean vector. And here we go, we make samples. Just going to make quick work of it. There we go, it's fast. And then we're going to drop these samples and create a prediction. Now the prediction here is really, really simple. It's a simple model. It's just saying that the prediction is use these mu's and sigmas in the sample. I want to show you a little bit what's in samples first, though, so you can see exactly. And this is, again, how you play with this. It created a bunch of mu's and sigmas. Why? Because that was the name of the two items inside a par mean, mu's and sigmas. Some are going to be running around 6, and it's going to be running around 2.0 something. All right. That's what we just created. Now the prediction is, pop all of these numbers for each pair, literally each simulated hypothesis, samples, how many of them are there? We don't have to count them, and we call it n of open and close parentheses. I think there were 10,000. Yep, there we go, 10,000. create normal random variates. Okay, normal variates. So here we go. And we got prediction. Now let's look at samples again and see what that mutate does. It adds another one. Somehow I got these to be, well, the Tibble does it, 2 decimal places. Okay, so now we have mu, sigma, and a prediction. We have the parameters and how they vary, and prediction and how it varies. So what's your guess? Will these vary more than these? Well, you should be able to think about that because we calculated the standard deviation of mu and the standard deviation of sigma, remember. It was 06 and 04, 04, 06, I can't remember. That doesn't matter. We're going to have this. We're going to use CODA to help us. MCMC makes this Tibble into a MCMC class. Markov chain Monte Carlo. Look it up. MARKOV. Yeah, Markov chain Monte Carlo. Okay, and now we're going to be able to do this with CODA. It's taking a while. Why? 10,000. My goodness, this is the prediction. It's one of them. Notice it produces what is called a rug underneath it, which are just points lined up. You can see it's very thick over here, and see they thin out in the tails. There's a couple of stragglers over here in the simulation. That's the density of sigma, again, between different numbers. And the density of mu. Ooh, it's kind of good there. Okay, basically, these are going to be normal distributions. Well, that's pretty interesting. We just did our first, well, I would call this pretty close to being a professional version of a system here. I created a little, I did this more because I wanted us to learn some more R. I made a helper function to build a high probability density interval. Oh my God, I'm going to get in trouble for that. Density probability. I'm going to change it everywhere now. I have seen it probably in error. These are probability intervals. High density means find the map, the maximum a posteriori, and work out in each direction what 89% means in this case, or that's going to be the default. I'm going to use a different one, 91. Both are prime, right? Yeah, okay. This here, density probability. I think that's the right way to put it anyways. Okay. Oh, see, they do high probability density interval here. That's why. Doesn't matter to me. Either way works. Put X files there. I don't care. And I return a function that creates something that looks like this. Okay, first of all, I've got to skip out of that. I made some sort of boo-boo here. No boo-boos allowed. Okay, that green went. Good. There we go. I wanted to make a table like this. So that's what I had to do. And I'm using some tricks of the trade. I'm doing an evaluation. See, what I wanted to do was make a function. Give it the column names. That was mu, sigma, and prediction. I want to make them row names now. Give them column names and perform this for each column name. Well, you're going to drop that column name here, concatenate it with sample samples this. So if you take, oh gosh, samples mu, okay, you get all those. Okay, HPDI of samples mu gives us that. Okay, on 8989, that's the piece there. That's the McElwreath version, and this is out of Coda, which is what McElwreath uses. And I can't use it because I have to do something else. I gotta make this MCMC of that in order to finish my little, there we go, lower and upper. And they use 95%. If I did this, if I did this, I get the 89%. It's a little prettier this way. This is the way Richard McElwreath does it, or close to it. I don't think he uses lower and upper. I like the lower and upper because when I'm explaining this again to another humanoid, I want them to see it straight out. Tables are visual. Tables are visual. Okay? Not just graphs. Tables are visual. We're going to talk about regularization eventually, but not today. Oh, I love regularization. And now we're going to do a plot of the same, using a histogram this time, and two vertical lines. I'm using labs, title x equals y equals subtitle. You can do all of that. And there we go. There's my posterior predictive distribution. Now we can say we have done Bayesian inference between these two, and we can put in these with text annotation text. We know how to do that. We can actually load in there the numbers. Oh, notice I said the x-intercept is HPDI samples. Oh, that's kind of interesting. I changed my, well, I gotta be so careful when you do this. Okay, good. Notice the set seed is still that. Not that I need it. There we go, same thing. Why do I use 3, 1, and 3, 2? Well, if we go back up here, prediction is row 3, column 1, row 3, column 2 for lower and upper. So the 3, 1 and the 3, 2 index where those numbers are coming from. And notice we can deposit them very nicely in here. And now we have something that we could say, well, we could use this for work process somewhere, some sort of workflow. And we just built this. Now, is there an easier way? Thank goodness there is, using the slim version of the McElwreath beast called rethinking. No, it's not a beast. It's a very tame, very quiet, I think, a cat. His cat. It's a cat called Mishka. I've got 4 cats here. They're not even here. No, okay. Usually they're climbing all over me. And Moshe is one for Moses, and because he has whatever, don't worry, mustache. Um, Jesse and Zeke. Yeah, Ezekiel. We like the prophets around here. Um, let's see if I can get this. There we go. That's what I'm looking for. Here's our model. We're going to translate this into. I'm going to put this into there, underline, italicized. Um, Rethinking ease. It's a new language. Okay, it is a language, and it's parsed out in a thing called a parser, which I would love to show you the insides of. I modified his initial parser that Richard put on to Twitter before it became X. So it's really a Twitter reference, and I use it to play with some other distributions that I happen to have recently become quite infatuated with. The asymmetric Laplace distribution for the observational model for quantiles. There we go. Lots of fun. Although Roger Kunker, who is quantile regression along with Gil Bassett over at the University of Illinois in Chicago, he's wondering if we're already doing this with bootstrapping, and what if you know what that is? I'm not even teaching that these days. Why do you need Bayesian again? He's very probabilistic thinking himself, so he's a deep thinker in this matter. QUAP, S quadratic, QU approximation. I don't know how he came up with this, but it stuck. A list is a particular kind of list. It's listing this, comma, this, comma, this, comma. It is a list of things. And then it pulls it apart. It knows to use d-norm. It knows to link this mu with this. It knows to do a simulation. All right. It knows to do all of these things and create a likelihood function. The very one that we have actually is made from this much nicer thing. And now look at how close this looks to the math. This is what we try to do. The tidyverse is trying to look like SQL programs with verbs and nouns and adjectives, maybe an adverb or two in its language, with mutate and typing, and there's also sample this and n of that, and there's a summarize, there's a left join, a right join, a join, just like in database. Well, Richard's trying to do this with our language. Okay. It's just like the system dynamics language. XMILE is the standard for that, and it has a parser, and so on. So parsers are all around us. You should learn more about them. Not hard to do, rather interesting. We use parser information here with eval and parse. We parsed an expression, which was a string, and then it translated into something that R could understand and evaluate into a number. All right. And then the evaluation that's the evaluation. We get a number. We got the minus 2,300 something log likelihood. Was that what we did? Well, something like that. So let's run this. We're going to call this model 0. It's our very first model, but it's the 0th model. We specified data. We know what the data was. And we get the same numbers. The same, remember that was on the diagonal, the square root of the diagonals. It's the same mean. This gives us 89% probability difference between here and here. Very, very close. Very, very close. Let me do the 89 up here first. Okay, yeah. Yeah, look, very, very close on mu and sigma. 582, 605, 196. That's the 91. If I were to use 89, we're going to get exactly the same numbers, aren't we? Yes, we are. 604, 212, 197. Boy, they look so familiar. There we go. 97, actually 198. 4, 212, 583, plus some change. Okay, you get the idea. This is a lot easier to use. Also, it tells me the story immediately. The math story and the statistical story kind of combined here. I don't know, is that enough? No, I do something else down here, but we're going to come back to this, but I just want to run it with you. Here's some data on bean price inflation in two eastern provinces. Surveys from the FAO, the Food and Agricultural Association of the UN, also did standard deviations and correlations, rolling standard deviations and correlations. I want to see if one market affects another. That's predator prey. Well, predator prey is just a way of talking about two entities interacting. So it's really the interactive model. And you can see this is going to be a mess. This is not going to be very good. So we'll read in the data using a CSV file. We'll look at a summary of this. There we go. We see the ranges. There are a lot of zeros in one of these, and we're going to see that in a couple of seconds. We're going to create a new piece of data here. I'm going to call it data 0. Data 0. Watch this. Wow. Okay, lots of zeros. Okay, and this is Maniema, the province. These are really important in food security in a lot of cultures, and in the culture of our own household here, we rely on beans for a lot of our protein and broccoli and other cruciferous vegetables. But beans are a staple around the world. A gazillion kinds of beans and pulses as well, lentils and so on. Very, very important in the evolution of human culture and physical migration over time. Well, the blue ones here are all, I need to put a legend over here eventually. But the blue ones are Maniema and the red ones are, look how many zeros there are Skivu, the other one. And this is daily from about, oh no, I think this is weekly, actually. I just realized that we're going to fix that right now. I remember what I did. I made this data set. It's messy, isn't it? We like messy. We need messy because the easy stuff isn't what we ever see. This is what we see. So we're going to have to play with this a little bit. Play we shall. There we go. That's the week. Now, a lot of zeros there. And we'll fix this one here too. Not going to play with it. This is just playing with it. Instead of reading a table, I do stuff like this, and so should you. This is a scatter plot. There we go. Look at that. I would say there's different behavior to the left than to the right, negative versus positive. We might actually want to divide the data up into those two sections, one called left, one called right, whatever. And we're going to be able to do that with Richard McElraith's modeling using subscripts. And that'll be something we'll do next and play with that a little bit. because there's probably two separate models going on here, coming down here and the other going here. And we're just going to say nothing happens in the middle. Just look at that. This is almost like a distribution right here. You know, around the zero of m, s moves up and down. Matter of fact, that's probably a very interesting result in pricing dynamics. Probably it is. The rest of it's volatility clustering. Um, okay, now once we have that done, we can go through our stepwise process of asking questions. The first question there. What is the impact of bean price movements in one province on the other? We hypothesize a model. Okay, we're hypothesizing. Then we sampled, yes, and now we're counting the ways. It's coming up next. There we go. Now we have this model. The regression is here. The mean that's going to be dropped inside of this normal sampling for Maniema is an intercept, a slope, times whatever is happening in Skivu. Okay. Oh, and we will sample values from the intercept and the slope and run this a whole bunch of times. But actually, we're going to be finding the alpha, beta, and sigma that give us the best maximum a posteriori probability in terms of likelihood. Okay, the best. And then we'll simulate off of that. So we have our sample of data. We're all ready to go here. I'm ready to rock and roll this thing. But one of the questions we raise is, where do we get the 0, 2, 0, 2, and 1? Normal, normal, exponential. Well, that's the thing. It's not subjective beliefs. I don't use this analysis for subjective beliefs in this context. I use it to come up with the best description of the data. So it's very phenomenological. There's causality outside of this. That's the model. We built that inside of system dynamics. Predator-prey interaction models. That's the science. And then we're going to use this technology that we're developing here. It's a technology, something we're discovering and using and manipulating. Yes, we're making. For the purpose of calibrating our causal models, okay, our system dynamics causal models. So this part here, what are our prior expectations of this? Well, not expectations. What are the best priors that help with M and S? Well, we can do this. We can test some ideas. And, you know, we all know who've been doing this for a long time. There's no right, well, there's a couple of right or wrong things you can do, but not that many. This is a relationship between Maniema and Skivu, given a set of, this is the priors, this is checking the priors. And it kind of violates probably the, right here, these will violate it. We might want to put a line here and a line here for the max and min of Maniema and Skivu. Okay, but anything within right here looks pretty good. We still have some stuff outside. I'm not too worried about that actually. I can play with this all day long and not get much of a different picture, but you can play with it. You should, to see that for the most part, the priors are going to be within a range of Maniema and in a range, this range of Skivu. Okay? In other words, they're not going to violate it too egregiously. Okay, whatever that means. All right, so we rerun the model with 0.25 and 0.5, for example. By the way, I've tried this with a lot of different values, and they come up everything comes up smelling like the proverbial rose. Okay, same model as before. I think I changed DXP to 3. For some reason or other, didn't like what I did there. Also, I want to check one other thing. Always check your models. Yeah, D0. Okay, I'm using D0. That's probably why it couldn't find it, right? Because it used the wrong data set. Okay, so it's a D0 data set here. See if this works. First you don't succeed, try again several times over. Oh, that worked. Beautiful. And now we have a rough idea. How do you read these? Okay, that's what we want to do next. Now, in typical frequentist while, I suppose a probabilist while, meanwhile, what we would do is you take the mean divided by the standard deviation and do a t-test and 3 regions, accept, reject. No, we're not doing that anymore. What we're doing is we're looking probabilistically at where the alpha for M and the beta for M. I can write this out alpha. This is just standard way we do things, which is looks pretty close to 0 here. Very small standard deviation lies right in between a minus 0.02 and a 0.03. It's very close to 0 in here on average. It could go this low or this high. Okay, all valid simulations. This is the uncertainty. And we're going to make some very nice, with GG ridges, some very nice depictions of this movement back and forth when we get this. Okay. Richard McElreath also has some animations to show that. You might be able to produce an animation or two as well. Beta, on the other hand, the rate of relationship between one and the other, standard deviation, that's 2 to 1, that's good. That doesn't mean anything here. It's between these two. It's certainly not 0. There's no overlap with 0 in this probability interval, but the interval's pretty wide. This interval's very narrow, right around 0, very narrow. This one's a little bit wider. Okay, pretty good. And sigma's positive. It's somewhere between 16 and 19. It's at 17. Pretty tight here. Okay, tells me putting the right idea on movement, that's sigma, in the relationship. Probably the right idea on this 0 result, but probably we need to work on beta a little bit, although these aren't too bad. Okay, well, look at the next picture. You're going to see how much work we got to do. We can also do this. This is a nice pairs diagram where we have the 3 coming down here, the 3 parameters, and these are the correlations between the two. And you can see that, these are pretty indeterminate. They're very small, near 0. Anything less than absolute value of 0.1, this is a very tight relationship. And this is real data. Fascinating. But these give the marginal distribution of each of these parameters. Notice we get that range, this range for A, and this range for sigma. Sigma is pricing risk, actually. All right. And then here is a nice little routine to, let's take some samples from M1, the thing that we made. Remember, M0 was our initial model. We'll never use M0 ever again. Shrine it, put it up on the wall. But this is M1, model number 1. Extract samples put it in something called posterior sample, post. Create a function called link. And we're in McElry's book, page 107. I like the manual method. It's the method that we always used in various programming languages to do what we're going to do next. We want to put a range, a probability interval around our regression line. And we're going to do that. I don't even want to show it to you. It's just too good. But we create a function to calculate, it's just a little calculator, this mu link. Every time we call it, it's going to pull up something, one of the AM simulations and one of the BM simulations. Let's just look at what post looks like for a second and do a head of post. There we go. You can see it's 3 columns. And you can see there's 10,000 observations in each of the 3 columns. First column is alpha, second one is beta, third one is sigma. So it's just creating a regression line. Alpha, beta times S skivu. Okay. And then we create an equally spaced grid. And I'm going from the minimum roughly to the maximum of skivus, call it sequence of skivus data. Okay, so I'm using that. I'm making however many there are. I don't even know what that number is. Let me look that up. Bunch. Length of interesting. Oh, I got S and M. Okay, good. Very good. So that's what I was hoping. So the length of one of those vectors is 128. 128 weeks. Okay, good. And I'd forgotten what that was. Oh, there we go. 128 variables down there. Here's a sequence. Again, do this again, do this again, do this again. Okay. There we go. That's the thing I needed to do there. This again, this again, this again, this again. What happens when you change a single variable? I should always do what I'm doing here. Check it out. Evenly spaced between the minimum and the maximum. Okay, that'll make an interesting picture for us, by the way. And now we do something called apply, S-apply. S-apply will, simple apply or system apply, take this sequence for each one of these items, drop it into this piece up here. Okay. Drop it into what would be S. Okay. So the first one will be post this plus post that times point minus 0.7. Then it goes on to the next. This is a very, very fast calculation machine, which is otherwise a for loop. Okay, we don't need to do for loops here. And then these two do row-wise. Row-wise, or is that column-wise? I always forget. So if I forget, I do this. and look up what some of the details are. And the apply function uses a mu, make averages, and we want to make means actually, means, along one dimension. Oh, we don't have a good. Two indicates rows and columns. One for a matrix indicates rows, two indicates columns. So we're going to make it across columns. Okay, that's all good there. And so we're going to calculate those, and then we're going to calculate the probability intervals using the probability interval calculator inside of apply with a probability interval of 0.91. And this one's real interesting to look at. Mu pi. All of these. Okay, these are all 128 of them. Ahead anyways. Okay, let's look at the bottom ones. For each and every point, 128 points. It's going to give the lower and the upper. Lower and the upper. So you're going to be able to take the lower, and plot them all, and the upper and plot them all. Just like you can plot the mu mean, which are these 128. You can plot every single one of these. Positive. Okay. So that's very cool to me that I can do that. So I have the mean line. I have a different location, the plus and minus from the mean. And now we're going to put all of these together into a tibble. But because of the shape of the lower, the mu pi 1, and the upper, the mu pi 2, I have to transpose them. Please go look at that yourself as to why that works. I remember I should have done this. There we go. Probably should have called it P1 for model 1, but anyways, water under that bridge. There we go. And now I am going to create a plot. Okay, I'm going to give it a name P for plot. I'm going to take all of this data, dump it into this grammar of graphics approach. I'm not going to go through, but you can go through it yourself, because this is what I want to get to. What a mess. It's a big mess in here. So this model does not work. But these are the probability intervals. Notice it knows to pound it up and down and up and down around. It's totally different than this line. It's crazy. This thing doesn't work. Works a little bit here, but look, we have a different line here for sure. And this is how you diagnose odd looking things like this. Otherwise, it's a pretty good picture of a bat going around, or an eagle, I'm not sure. Okay. Not capturing the dynamics of this relationship. We do have a model that might capture it, so we're going to do that. We've accomplished an awful lot here. Okay. We've actually gotten to looking at a predictive probability interval, which tells us we're not good at all. We need to change this model. And we will. We will do a couple of things. This is called confounding. We have many different types of confounding in this model that we're going to fix with our ordinary differential equation model ultimately, but other ways as well. And that'll be all on the next installment. Hope you enjoyed this spree through data and lots to learn in terms of using R and thinking with R. Have been using R. I used S before and EPL and MATLAB and Fortran and Assembler over the years. This is pretty easy to use. And Python, I'll get Python. It came out when Pascal was going out. They give people like certain things and stuck with them. This is not Pascal. This is very functional oriented, which lines up very nicely with the thinking mathematically that I do inside of these models. So this is what I prefer. And the linkage, I get a good workflow with it. Like I can create a document right now. Let's see if this thing will create. It doesn't. I'm not going to worry about it because I'll go and play with it at another time. But it's important to go through these experiences piece by piece. If you don't know what T stands for, you'll look it up. If you don't know why we had to do a comma 1, that's the first column, versus comma 2, the second column, where all of the rows, well, you need to go back and refresh what you did before, learning a little bit of R. Okay, and this is taking some time. Interesting. There it goes. There it goes. Come on, you can do it. There we go. It's doing big simulations. That's why. As far as I can tell, this is all the work we just did. Oh, I love this. Yeah, good, good. Yeah, that's not going to work. We're going to have to make that, bring that over here somewhere. So there's something to work on. Yeah, probability. Yeah, yeah. Okay, nomenclature. Love it. Oh, good. I'm glad we caught this negative. Okay, so you look through your work. This is going to be interesting to play with. What is this? It'd be interesting to take a vector of mu's and a vector of sigmas, put it, see if it works inside of this. Probably have to use an apply function to create a surface, or given a level of mu, how log likelihood norm changes. That'd be a nice little exercise. Doing all of this. Now, I'm putting you through this vegetable sausage grinder because I want you to see what is in QUAP, what we have to do to get this. Okay, you never have to do this again, but it's good to know underneath if you run into an error, the optimization doesn't run, whatever it is. All of this is automated. I like this function a little bit better. All of this is automated down here. Nice plot. There's the easier way. It's all automated down here, and we ran our first regression as well, which I'm very excited about. Tell, right? Okay, check the priors. Oh, did all this good. Ran our first regression. So we've done a lot. We're going to run wolves on Mises, on moose as well. And we're going to see that some of it will work, and then we're going to modify that model for interactions. And we will see something remarkable happen. A little bit remarkable, anyways. Pairs, correlations. Serious R stuff going on here. More importantly, serious post-optimization analysis going on here to produce this very important diagram, which I think I'm going to frame this and put it up. It looks pretty cool, nice piece of abstract art. No, I won't be doing And I will leave you with that. Thank you very much for your kind attention. And I've taken up, I think, enough of your time uh, for this very first episode of week 4 as we count on Laplace all week long. Um, so expect to do some more of these. We're going to be using this model. We're going to be using a lot of this and a lot of this to get our job done. So we're going to have some very, very creative mu linking going on to get that job done. All right, I'll leave you with that. Always remember there's so much to do. Yes, take it in your stride, but encourage one another daily. Do it today. Do it today. And work together. Group participative transformation. Yes, GPT is way generative. Oh, it's very generative and very generous. You take care and see you in the next episode. Bye.